Pump math part 3. Friction loss.
Let's say this nozzle wants 30 psi to operate properly. Yeah, I'm making that up. To get 30 psi there, I start here at 40 because I lose 10 psi as all that water travels through the hose. We all know it costs energy to travel. It costs calories to walk, costs fuel to drive. For water traveling through a hose, it costs you psi. How much pressure we lose depends on 3 things: the hose itself, how much water we're pumping through, and the length of the hose. To calculate, we put those 3 things into an equation. Friction loss is equal to C times Q squared times L. The C is a constant, or it's the coefficient, and it's based on the hose size and type. The coefficient is a number that tells you for a certain length of hose what's the cost of energy to send water through it. C is essentially the extra energy it takes to get water through that particular hose. For this one, we're going to multiply what we got by 24. This we're going to multiply by 2, purely because of size. Let's say we're flowing water at 100 gallons per minute. Because I can fit less in this than at this at any given time, it has to go a lot faster through this. The bigger the hose, the less energy you lose, and the coefficient is smaller. It can also be affected by the age of the hose and what the lining is made of. For our purposes, we'll use the generic numbers from the book, which are these. And if you're wondering about this goofiness, 3-inch hose can either have 2.5-inch couplings or 3-inch couplings. If you don't have a specific coefficient of friction for your hose, just use the values from the book. And all you need to find them is the diameter of your hose, and maybe your couplings. The Q stands for quantity. Q you can think of as quantity or as throughput. It's how much water over how much time. In the US, we use gallons per minute or GPM. Let's play with Q a little bit and see what the impact is. So with pretty gentle pressure, 1, 2, 3, 4. I can empty it in 4 seconds. Let's see what it takes to get down to 2. 1, 2. To empty this in half the time means I doubled my Q, but it took way more than double the pressure to get it done. So as my Q increases, my friction loss way increases. L is for length. It's the length of your hose in 100 feet. This is bucatini. It's a tiny straw. If I try to blow through a little section, I can. Twice the length, twice as hard. Double it again, twice as hard. And it makes sense if you think about it. When you double the length of travel, you worked this hard to get this far, then you work that hard again to get that far. That's the idea, so let's put them together and do the math. We've got 200 feet of 1 3/4 hose flowing 150 gallons per minute with a fog nozzle. So to calculate friction loss for the hose, we know we need C, Q, and L. And I like to write out what I know first. Anytime I'm working on a problem, I like to draw it out first. My GPM is 150, which is Q of 1.5, because Q is in hundreds, so we just divide by 100. So we know the length is 200, that's our L. We just need to divide it by 100. L is 2. And now C. So C is our coefficient. It's based on our hose diameter. So we go reference our table over here. For a hose diameter of 1 3/4, our C is going to be 15.5. So I plug that in here, and then I plug those into my equation. C times Q times Q times L. So I plug these into there. So it's 15.5 times 1.5 times 1.5 times 2. Plug that all into my calculator, and I get 69.75. And we're going to round that up to 70. So 70 psi is the amount of friction loss in this stretch of hose. Remind me, why are we doing this? When you're running the pump, you have to remember that the pressure you see here is the pressure measured here before it travels through the hose and to the firefighter on the other end of it. If they need 100 psi to make sure this nozzle does what it needs to do, you've got to provide enough pressure at the pump to make up for all the losses between the pump and the nozzle.